Uh, Good afternoon. My name is Rodney Boyd, a senior computer science major at Morehouse College.
And I am Kazimba Kennedy, also a senior computer science major at Morehouse College. We're about to present our project for software engineering. At this point, we are going to share our screen so that we can go through it. That's good stuff. So just 20. Okay. I'm sure you can see.
All right, so the title of our project is Induced Electromotive Force, EMF for short. The introduction. Michael Faraday came up with Faraday's law of induction. Induced electromotive force, or EMF, results from a change in magnetic force over time. EMF is measured in volts. Magnetic flux is measured in Tesla. Time is in seconds. Most common way of showing EMF is with a coil and a magnet going into the coil to demonstrate the, as well as a voltmeter to show the change in the EMF. Project overview. Through Greenfoot, we recreated the Faraday's experiment. We set up a magnet and a simulated image of a current for actors. A station was set up that had a coil connected to a battery and a voltmeter. Sliders were used to adjust the variables, the speed of the magnet, and the EMF change with the sliders variable. Induced EMF equation. EMF is calculated by taking the number of turns of the coils and multiplying it by the change of magnetic flux over the change in time. This value then becomes negative because of Lenz's law. It says that the current produced works to oppose the magnetic field being produced, hence the negative. Schematic. As you can see on the right-hand side of the screen is a screenshot of our project. So we set up use of Greenfoot World. Actors are magnets, current, and sliders. Station is stationary, coil, battery, voltmeter. Sliders are adjusted by the slide hand that then display the value of that slide hand at the time. Magnet is set above the coil. Current is shown in the middle of the voltmeter. EMF is shown towards the right. Can be calculated during the program being run. So with that, if you simply press the enter key where you see EMF, it will then display what the current EMF is at that time using the equation we showed you earlier. Showing EMF. We use interactive slider actors to have users able to input. We found this more conducive opposed to users entering random numbers that may not be correct. It was a way to guarantee a correct output every time. Sliders were set at a range between 1 and 100. The EMF increased quicker visually the higher the change of magnetic flux slider went. The EMF decreased quicker visually the higher the change of the slider went. Change of time slider went, and the EMF also increased quicker visually the higher the number of coils was set. Magnetic madness. Factors affect how fast the magnet magnetic input, the faster the magnet goes in. The smaller the change in time slider input, the faster.
User interaction. So, as Rodney mentioned earlier, the users can also press the enter key based on the values of the slider at the time. So the default EMF value would be -1. Sliders are all set to a default of 1. Lenz's law. So this would testing. We had to make sure that lots of things worked before we could say that the project was ready. So first, we had to make sure the sliders were set to the right initial value, which would be 1. We needed to test the range of motions of the sliders when the program integer values only. The EMF should become more visible quicker when the change of magnetic schematic, it grows, and the higher you set that magnetic flux slider, the faster it grows. EMF should become that works in opposition. As you increase the change, as the change of time is increased, the EMF is going. Dot becomes a line as it grows, and it shrinks as a line when you raise the time slider. EMF should become more visible quicker when the number of coils turned slider is increased, which works similarly to the change of magnetic flux slider. We also needed to make sure that the magnet should not move when the number of coils turned slider is increased by itself. If everything else is, it shouldn't move. The magnet should move quicker as change in magnetic flux slider is increased. The magnet should move slower as change in time slider. The magnet is moving for the time slider is when the value is at its lowest point, because the time is in the denominator of the equation. EMF should be displayed as a double type variable when enter is pressed during running the program. We figured double would be the best way to go about it, so you don't have to, so your value could be a little bit more accurate. You don't just want an integer. Some design and analysis. On the right-hand side, you'll see, again, a screenshot of the code to set up the world. This sets where the objects are going to be initially based on their X and Y coordinates. So such a slider would need a starting value of 1 and necessary because we needed to reference objects from other classes. Able to refer to an object from the slider class equation, as well as make the magnet and current change. On the right, again, you'll see code. It scales the picture. The picture that we have from online of the current, the circle, it was bigger than needed to be, so we decreased segments that are useful and to visually increase. It's between a range of 1 and 25, then you're going to increase the height of the current by 1. If it's between 26 and 50 of magnetic flux. Also, it shows objects being methods are coming from, and then you interact. You can see down at you, because that's the in at the beginning of the equation, and the amount to slider in that enter public void. Then the image did is slide voltmeter, and the current is this yellow. Uh, it gets just reset. Change the ticker, the lower. You can show that and the change in time. The magnet's still moving. Balances. And we can then show the number of coils. Right, is increasing. Shown. So here, time goes up. For pretty much for our project. Unshare this to see when you're sitting.
Yeah.
Really good thing.
And thank you. Verizon. Please review